Welcome to this new video. So before I start, let me tell you that I will be posting more than at least two videos per week in order to finish on time. So I will try to post them on Wednesday and Thursday. Okay. So this is the second video for this week, and in this video I will finish the lecture of chapter 2. So I will end with the homotopic version of Cauchy's theorem. Okay, so consider two loops, okay, in a subset of C. How to give a meaning to the notion of deforming the first loop into the second one. So here by deformation, I mean all the transformations are allowed: rotation, symmetries, squeezing, stretching, anything you like, except breaking the loop, okay, which introduces a discontinuity. So this idea of continuously deforming an object into another object is, well, we saw it in the context of continuous functions in general, but here we want to connect two loops with a family of loops, if you like. So this is the definition. If you have two loops, gamma 0 and gamma 1 in omega, we say that gamma 0 and gamma 1 are omega homotopic or homotopic in omega. It's important to precise. I will tell you why in a moment. If there exists a continuous function h of two variables, so it's the function from the square 0, 1 to omega, such that two conditions hold. Okay, so h of t0 equal gamma 0 and h of t1 equal gamma 1, and the second condition, h of 0 and s equal h of 1 and s. Okay, let me explain in more details what do I mean by what's the geometric interpretation of this. If we set gamma of s of t equal h of t and s, then we can think of h as being a family of loops because of the second conditions. Gamma of s is a loop because gamma s of 0 equal gamma s of 1. So gamma s is a loop. And the first condition is that gamma 0 of t equal gamma 0 of t and gamma 1 of t equal gamma. So actually h is a family of loops connecting gamma 0 and gamma 1. So try to draw a picture. Actually, pictures are taking a lot of time here in LaTeX. So I will not draw anything in this video, but I will draw something if you like when we meet on Zoom by the end of the course, if you like. So I may draw you more pictures. So a homotopy in omega, it's very important to precise that h takes values in omega. Okay? So a homotopy, if you like, is a family of loops connecting loops, two loops. Okay? Or you can think of it another way as a path in the space of loops. Okay, so I'm connecting two loops. I'm deforming one loop into another one in a continuous way without breaking the loops. Okay, so all kinds of operation or transformation that do not break the objects are allowed. So as I said, we can stretch, squeeze, rotate, translate, anything you like, as long as you don't break the object. So this is the requirement of continuity. Now, you may check that the homotopy is an equivalence relation between loops. Okay? And by the way, you will study in more details the notion of homotopy next year in the course of algebraic topology. where omega will be any topological space, not just a subset of C. Okay? And the second remark I wanted to say is that in the terminology of algebraic topology, this is called a free homotopy. Why? Because usually the homotopies considered in algebraic topology are based at some point. So all loops have a common point, actually. But we don't need this restriction here and later. Okay, so this is called a free homotopy. You just call it homotopy. Okay. Now, the first remark and the first example is that any two loops in C are C homotopic. Why? Because I can connect the two loops gamma 0 and gamma 1 by what we call a straight line homotopy. So when S is 0, we are at gamma 0. When S is 1, we are at gamma 1. Okay? And you can check the second condition because gamma 0 and gamma 1 are loops. So this is the simplest possible loop, a homotopy connecting two loops. Now, if this is true, you will tell me, well, then this is all, everything is trivial. Since I can connect any two loops by a straight line homotopy, then I don't need this concept, actually. Well, but pay attention to something. In order for this, note that omega should take values in, H should take values in omega. This is the point. If omega is convex, then this straight line homotopy takes values in omega, because omega is convex. But if omega is not convex, then this is not a homotopy in omega. Okay? So everything depends on the geometry or the topology of the domain. Okay, so the notion of homotopy actually was introduced to make sense or give a meaning or quantify the notion of holes in a domain. Okay? So, and we shall get back to this idea later, actually. There's a whole branch in topology that studies the notion of holes in topological spaces and surfaces and so on. And it's called algebraic topology. Okay, so note that we encountered the notion of a domain having a hole inside. Okay, so there's a big difference between. So the topology of the domain actually is very important to us. Now, if omega is convex, this is the trivial topology, actually. So any two loops are homotopic, there's no hole, so it's trivial. Okay? But things become more interesting when we consider more general domain. Okay? So these two examples are trivial. Now, third example, consider the circle traveled once, okay, of center 0 and radius 1, and the circle of center 0 and radius 2 traveled also once. Now, of course, these two loops are C homotopic, but they are C star homotopic. Why? Because if I connect them by the straight line homotopy, the straight line homotopy, as you may check, does not pass through 0. This is the point here. Okay? So there's a big difference between C and C star topologically. C is topologically trivial, if you like, in the sense that it has no holes. But C star has one hole because I removed 0. So there's a big difference here. So the straight line homotopy connects these two loops in C star. However, if I take gamma 2 to be E2IT, so which means this is the same circle but traveled twice, is gamma 0 C star homotopic to gamma 2? No, because gamma 0 travels winds one time around 0, whereas gamma 2 winds twice. So we see intuitively that we cannot deform gamma 0 into gamma 2 without touching 0, without passing through 0. So they are C homotopic, but not C star homotopic. And I will give a rigorous proof later. Okay. Fourth example, consider the circle, same circle gamma 0, and the circle of radius 1 and center 2. So they are tangent actually. Okay. They are, of course, C homotopic, but are they C star homotopic? Can I go from the circle of center 0 to the circle of center 2 by in a continuous way without touching 0? If you think of it, you will convince yourself that it's not possible because 0 is inside the first circle. So if you want to go to the second one, at some point you will have to pass through the origin. Okay, so the straight line homotopy will not work. And once again, I will give a rigorous proof later. Okay, so there's no C star homotopy connecting gamma 0 to gamma 1. So there is a hole actually. This is, or an obstruction if you like, that prevents the existence of a homotopy in C star. Okay. And now, having defined the notion of homotopy, I can state the main theorem of this section, which is the homotopic version of Cauchy's theorem. It states the following. If two loops in omega are homotopic in omega, and f is holomorphic on omega, then the integral of f along gamma 0 and gamma 1 are the same. Okay, so otherwise stated, if we deform continuously our loop in omega, the integral does not change. It's very important. Think of it. Okay, so I will not prove this actually because I will have to. It will take some time actually. I will have to introduce 4 lemmas, so it will. We don't have enough time. But if you are interested, you can read the proof in the notes of Math 307, the older course. It's on my website. Okay, but the idea is that if you perturb a little bit gamma 0, first result actually, we can prove that if gamma 0 and mu, for example, are close enough, then the integral does not change. Can prove that. And then by iteration, so we take a loop close to gamma 0, close enough to gamma 0, and then we connect, so call it gamma 2 if you like, and then if gamma 3 is close enough to gamma 0, so we can connect actually gamma 0 and gamma 1 by a finite sequence of loops, and the integral is the same on 2 consecutive loops. This is the idea. Okay, so in particular, if you have a loop and you perturb it a little bit, you change it a little bit, you deform it a little bit, the integral does not change. But if this is true, then we can prove that the integral does not change under any homotopy, provided we are still in omega. Okay, now in the remainder of this video, I will draw some conclusions of this theorem. Very important. So first corollary, if we have 2 loops, gamma and mu, in omega, that are homotopic in omega without A, so there is a homotopy taking values in omega without A, connecting the 2 loops. So of course, gamma and mu do not pass through A because the homotopy does not pass through A. Then the 2 loops have the same winding number around A. Why is that? Because the function 1 over z minus A is holomorphic on omega without A. because Z is different from A on omega without A. So this is the inverse of a holomorphic function that does not vanish, so it's holomorphic. And by Cauchy's theorem, the integral is the same along gamma and along mu. So when we divide by 2 pi I, we just get the index. It's very easy. And now I will use this corollary to prove the examples, to prove examples 3 and 4, that two loops are not homotopic. Okay, so if we take the loop that travels once around, the circle that travels once around the origin, and the circle that travels twice, E to IT, then they are not C-star homotopic. On an intuitive level, we understand why, because this one's once, this one's twice. But we have the notion of index that precises this. So the index of gamma 0 with respect to 0 is 1, as we saw in a previous video. However, the index of gamma 1 is 2. So since the two loops have different indices, they cannot be homotopic in C-star. Okay. So this is the rigorous proof. And what about the circle traveled once in the positive direction and the circle traveled once in the opposite direction? Also, they are not C-star homotopic. They are C homotopic once again, but they are not C-star homotopic. Why? Because the indices are opposite. The index of gamma 0 is 1. The index of gamma 1 is -1 with respect to 0. So they cannot be homotopic in C without 0. And last example, when we took the EIT and 2 plus EIT, so two tangent circles, if you like. Now, we know we can prove rigorously why they are not C-star homotopic, because the index of gamma 0 with respect to 0 is 1, whereas the index of gamma 1 with respect to 0 is 0, because 0 is outside gamma 1. It's in the unbounded component. And now, having introduced the notion of homotopy, we can define what we mean. We can give a meaning to the notion of a domain without holes. What is the difference between a domain with holes and a domain with no holes? In C, at least. Here we are talking about two-dimensional holes. So actually, the difference is that if you have no holes, then any loop can be contracted or deformed to a point, right? Or can be shrunk to a point. And this is captured by the notion of homotopy. So if you like, in a domain without holes, any loop is homotopic to a point. And we call this, in this case, if this is true, then we say that omega is simply connected. So simply connected intuitively means that, in C at least, in the plane, simply connected, it means that there's no holes. Okay, so any loop is homotopic to a point. Now, if there is one hole or more, or at least one hole, then it's not true that every loop is homotopic to a point. Okay? It's important, actually, the notion of hole, because it changed everything, as we shall see. And we shall see in a moment why this. So the notion of existence of holes is actually a topological notion. Okay? And we quantified it with the notion of homotopy. Okay? But this notion of a hole is true actually for just the subsets of the plane. Okay, because if you want to work in higher dimensions, actually, you would have to So, for example, if you take a ball in 3 dimensions and you remove its center, it has a hole, but it's simply connected according to our definition because you have an extra dimension, so you can deform the loop without touching the center. Okay, so the notion of simple connectedness actually means that it has no hole, but provided you are working in the plane. Okay. Now, every convex set is simply connected. Why? Because we saw it's trivial, because we can connect any loop to a point by a straight line homotopy. Right? It's very easy. C star is not simply connected. Okay? We already know why. Because if you take the circle is not homotopic to a point in C star. Okay? The annulus is also not simply connected. Okay? Now, we may have loops in the annulus that are homotopic to a point, but not every loop in the annulus is homotopic to a point. Okay? I will draw pictures later, actually. And now we have the necessary tools to answer the question, to solve the problem of the existence of antiderivatives. Recall that at the beginning of this chapter, we raised the problem of existence of antiderivatives, and we saw that not all functions possess an antiderivative, right? And I told you that we need 2 conditions. I said that before. We need a condition on f, and we need the condition on the domain of holomorphy of f. So here's the first result. If omega is simply connected and f is holomorphic, then f has an antiderivative on omega. Okay, so we have 2 conditions. And the condition of holomorphy, as we saw in the previous video, is a necessary one. Okay, so we have a condition on f, which is holomorphy, and we have a topological condition on omega. So omega should contain no holes. If you recall the example of 1 over z, which is holomorphic on C star, we saw that 1 over z does not possess an antiderivative because there was a defect in the domain of 1 over z, which is C star. C star is not simply connected. Okay, so why this is so? Because if you take a loop in omega, gamma, then because omega is simply connected, then gamma is homotopic in omega to a point z0. And therefore, by Cauchy's theorem, the integral over gamma of f is equal to the integral over the constant loop. When I say that omega is homotopic to a point, by a point I mean a constant loop. Gamma t is z0 for all t between 0 and 1, let us say. Okay, so by a point I mean a constant loop. So the integral over gamma is the integral over the constant loop, which is 0. And now, if you recall theorem, I think 2.1 was called 2.1. Our first theorem, actually, in the beginning of this chapter, f has an antiderivative, right? Because the integral over any loop is 0. So, and in some sense, this is an optimal result. Why? Because there is a difficult converse to this. It's in the, you can find this result in the book of Rudin, theorem 13.11. If every holomorphic function on omega has an antiderivative, then omega is necessarily simply connected. Okay. So in some sense, this is the best topological condition that we can put on a domain in order to ensure that every holomorphic function has an antiderivative. So we see here how topology interferes or interacts with analysis to solve some difficult problems. Okay, this is one of the reasons why topology is important in analysis. Okay. And this is not actually this is just one example. I can give you more examples if you like. So topology makes sense, actually. Topology is important. It's not just a difficult and useless discipline. And by the way, we already encountered another example of topological ideas in analysis when we talk about connected components. I hope actually that you solved the problem that I gave you not last time, the time before, about arctangent t plus arctangent 1 over t. Okay, this is just a simple problem of calculus, but the topology of the domain is very important. If the domain has two connected components, then we cannot say that f is constant. Okay, so okay, and okay, now next result is a particular case of a simply connected set, and so we have a notion between convex and simply connected. So we know that convex implies simply connected, and the converse is not true actually, because we may have a non-convex set which is simply connected. Okay, try to draw something actually which is not convex but simply connected. It's not difficult. Now there is an intermediate notion between the two, which is the notion of star convex or star shaped. Okay, try to draw your childhood figure of a star, right? That's 5. You draw it. And consider the point in the middle. And try to join the point in the middle to all points in the star. Then you have a point that can be connected by a straight line segment to all points of your domain. If the domain possesses this property, then it's called star-shaped or star-convex, because it has the same property as a star. You draw the figure or use your imagination. This notion actually is intermediate between convexity and simple connectedness. So a convex set is necessarily star convex with respect to any of its points by definition. Okay, so the converse is of course not true. You can just give a simple example, because the star that you draw is not convex, but it's star convex. Difference. And if you remove from the plane the negative real axis, then the resulting space is star convex. Try to draw a figure. So you have the plane, remove the half a line, and take the point of 1, right, or 1, 0. Then you can join 1, 0 to all points of C without R minus. Once again, draw a figure and convince yourself that we get a star convex domain. But it's not convex, of course. And more generally, if you remove any half line from C, then the resulting space is star convex. So you take a point in the other half of the line that you didn't remove. Okay? So we see that convex implies star convex. And now it's easy to see that a star convex set is simply connected. Why? Because we don't have the straight line homotopy, but we have something very close. Okay? Connect a loop to a point by this straight line homotopy, joining the loop to a point A, with respect to which omega is star convex. Okay? This makes sense because this loop, so H, is an omega, because the straight line segment joining gamma t to A is always an omega. So this makes sense. So we have convex implies star convex, and star convex or star shaped implies simply connected. And the reverse inclusions are not true. Try to give an example of a simply connected set which is not star convex. Just draw a picture. Okay? And next result is Cauchy's integral formula, the general version of Cauchy's integral formula. Okay. Note that we proved a particular case before we proved the analyticity of holomorphic functions. And now we can state the general version. So if f is holomorphic on an open set omega, and A is a point of omega, we have two things. If gamma and mu are loops in omega that are omega homotopic, and of course not pathing through A, then 1 over 2 pi I times the integral over gamma of f of u over u minus A minus the same thing over mu is just f of A times the difference between the indices. Okay. And the second conclusion, which is we shall use more often, actually, this one. If gamma is a loop not passing through A and homotopic to a point in omega, then I have a representation of f of A as an integral. So 1 over 2 pi I times the integral over gamma of this quotient. Actually, it's not 0 because this function inside is not holomorphic. It has a singularity at A. Now, f does not possess a singularity at A, but this ratio has a singularity. So I cannot say that it's 0 unless A is on the unbounded component of gamma, actually. So this integral is the index times f of A. And now the version that we proved before is in the case of a circle containing A in its interior. So this is 1 and positively oriented. So the Cauchy's integral formula that we use is a particular case of this more general, because here gamma is any loop which is just homotopic to a point in omega. Okay. Now, if A is outside the loop, this cancels. So the integral is 0. So otherwise stated, only the points inside the loop counts, actually. Okay. So when you have to evaluate an integral of this form, let us say, you only care about the points inside, the singularities inside. Okay, now this is not difficult. This is just a consequence of several things that we proved. So consider this function, Newton's ratio at A, if z is different from A, and of course f prime of A at z equal A, because we want a continuous function. Now, if you consider this function g, then okay, f is holomorphic, so holomorphic over holomorphic is holomorphic. So it's holomorphic on omega without A and continuous at A. And in the last video, actually, we know that G is actually holomorphic on omega. So since gamma and mu are homotopic, then the integral is the same by Cauchy's theorem. And now, if we already did something similar, actually, we split the integral into two parts, because G is just the Newton's ratio, because the U is different from A, because the loops do not pass through A. So G is just f of u minus f of A over u minus A. And since f of A is constant, does not depend on u, I can put it outside the integral. So the left-hand side here is just the first integral, and this is the second integral. Okay, and we did something similar. But now we are almost done, because this integral has a name. It's 2 pi I times the index. Same thing for here. So when we divide by 2 pi I and do the difference, we get the result. And the proof of the second conclusion is actually this can be proved along the same thing. But we cannot pay attention that we cannot deduce the second result from the first one. nor the first one from the second. Okay, so but they have the same a similar proof actually. Okay, because if you want to take this as 0, then we must have that mu is homotopic to a point, but mu is not necessarily homotopic to a point. Okay, it's gamma which is homotopic to a point. Okay, and final result in this chapter, Cauchy's integral formula of order n. So same assumptions, we have a holomorphic function in omega, and we have a point in omega, and we have a loop in omega not passing through A, because otherwise the integral is not defined. Then we have a representation of the nth derivative of f at A. So same thing actually. So the index of gamma times A with respect to A times the nth derivative at A is given by n factorial over 2 pi I times this integral. Why is that? Just go back to this form of Cauchy's integral formula, which is this result actually is useful when we deal with Laurent series, okay, but this is more often used. If we let A vary now, because this is true for any A, as long as it does not pass through, does not belong to gamma. If we fix everything and let A vary, then this is an integral depending on a parameter. And the function inside is continuous in both variables and holomorphic with respect to A. So the derivative of the integral is the integral of the derivative. So when you differentiate one time, you will get actually 1 over u minus a squared, because minus minus cancel. If you differentiate another time, you'll get the 2 and so on. So when you differentiate n times this formula, you will get this result. So the n factorial actually comes from the differentiating 1 over u minus a with respect to a, not with respect to u. Okay, and I will leave you now with a beautiful application of Cauchy's formula of order 1, first order, or 0 order actually. So because it's just f of a, not f prime. Okay. Here I'm suggesting that you always start by drawing a figure. So we have a half circle, so the diameter minus RR, and then the upper half circle CR. So it's a loop actually. We orient it positively. So first question, integrate EIZ over 1 plus Z square over this loop by using Cauchy's formula. So once again, okay, what are the singularities of the function inside? This is what you should start by considering. What are the singularities of the function? The EIZ has no singularity, but 1 over 1 plus Z squared has two singularities, which are I and minus I. So, and once again, if only the singularities inside actually matter. If you consider the upper half circle gamma R, then if R is bigger than 1, then I is inside. Okay, so you have to factor this and apply properly Cauchy's formula by stating all the conditions. Okay, and from this, and let R tend to infinity, and then deduce this. Okay, this is, we already encountered this methodology before. Now, the path once again is not unique, as Steve observed, because nothing prevents us of integrating along the lower half circle. But then it's interesting actually. Try to do both. You will have to pay attention to the orientation. Okay, so the index will become -1, not 1, and this is interesting actually. Okay, so try to integrate on the two circles, the two half circles, and If you pay attention to the orientation, then you should get the same result. Okay, I will correct that next week, but try to do it on your own. Okay? And I told you, I think that I'm planning to make a Zoom session with you by the end of the course. Okay, so prepare your questions and see you soon.